All right, so new topic. We're going to talk about counting. We're going to talk about counting for the next whole week. And then the last week, we're going to switch over to number theory and things that relate eventually toward public key cryptography, to the way you send credit cards over the web and not lose your shirt. But this week is all counting. Right? You have a week of this, so it's a quarter of a semester's worth. I need to tell you right up front, and this is true of every single topic in this course, you can take a whole course just in logic. You can take a whole course just in circuit design that relates to Boolean algebra. You can take a whole course in combinatorics. You can take another course in it, and then you can take a graduate course in it. Right? Combinatorics is counting. We're doing a quarter of a semester in it, so you're going to get the tools of combinatorics. You're going to get the rudiments. Some of it will sink in right away. Some of it will take some time to sink in. But this is the beginning of a long, long branch that you could follow much, much more deeply. But you will get all the basics that you'll ever need to do 98% of the things that come up in computer science. All right? So that's our goal. And I want to organize this discussion about counting in the following way. I want to give you what I think, in my experience, is the general bag of tricks that I've discovered over the years that come up a lot. Right? In this bag of tricks are conceptual things, ways of thinking about problems, and in addition, kind of the ABCs, kind of like the basic, okay, I can do that problem because it's a basic problem. You know, so there's conceptual ways of going about solving, and then just basic tools. And the combination of those will help you solve almost every problem that you'll see at this level. So what are these general principles? So one is this principle called the multiplication principle. I'm using this name because the book uses this name. Rather than define anything, you can go look at your book if you want to look at definitions or formal ways of doing things. I'm going to go through this introduction to counting mostly through examples. And then you'll learn the principle by the example, and then you'll just be able to apply the principle to other similar examples. But here's the idea of the multiplication principle. Let's say I spin one die, right? Regular six-sided die. There's 6 different ways that it can land. It's kind of an easy counting problem. 1, 2, 3, 4, 5, 6. Count the number of faces on the cube. But if I spin 2 dice, how many different ways are there for the outcome to show up? Well, there's 1, 1, and there's 1, 2, and there's 1, 3, and there's 1, 4, and there's 1, 5, and there's 1, 6. There's 2, 1, 2 through 6, 3, etc. So altogether, there's how many? There's 36. And the multiplication principle is an overwhelming idea that when you do 2 things, one after the other, in order to accomplish a complete task, then if you want to count how many ways there are of doing the complete task, it's the number of ways of doing the first part times the number of ways of doing the second part. It's very logical. Everything in combinatorics is logical, but some of it is very, very deep and subtle, and it takes time to digest. So, how many possible results when you spin 2 dice? 6 times 6. You don't have to use the multiplication principle here. You can make a little table, 1 through 6, 1 through 6, and notice that every little entry in that square table is another pair of dice spins, and 6 times 6. But it's part of a more general principle. Another example of the multiplication principle that you've seen before in your problem sets. How many ways for this class to get in line? In line, online, I don't know. It's New Yorkers say online. Or in line? New Yorkers say online. Get online. Anyway, what if you guys had to all get online and you had to go ahead and line up to use the soda machine out there? Right? So I can say there's 36 people here today. There's 36 ways I can choose the first person online. Now I have to choose a second person, and there's 35 ways to choose the next person. When I'm all done, I've accomplished my task. How many different ways were there for me to do this? It's 36 times 35 times 34 times 33. It's the same kind of principle. And the answer is, in this class, since we have 36 people, it's 36 factorial. If I change the problem a little bit, and I said I don't want you to line up, but I'm randomly 36 different times going to choose somebody from this class, and let them go out and, I don't know, check the doorbell or something, then I have 36 choices every time. I can pick the same person twice in a row. So then it would be 36 times 36 times 36 times 36, or 36 to the 36th. Right? So not everything's n factorial. Some things are. You'll see factorials a lot. They come up a lot in a lot of different disguises. You can prove things like this by induction. Here's a theorem from 1321. It's not written like this, but it means this in algebra. If Pn is the number of different ways to order n people, then Pn is n times the number of different ways to order n minus 1 people. And this theorem is written out in prose. It's written out in the vernacular. It was written in Hebrew. And it's a paragraph long to define these terms, and then 3 lines to quote this theorem, and then another 2 pages to prove it. And if you actually look at that recurrence equation, because that's what it really is, and you solve it, and P1 equals 1, then you get Pn equals n factorial. Right? I'm not going to go in that direction, because that's what we did last week. That's not our topic today. All right, so that's principle 1. Next principle, addition principle. These 2 principles are very basic, and the principles are going to get a little harder as we go along. Again, I want to do things by example. So how many ways to spin an odd sum? You spin 2 dice. How many of them give you an odd sum? Well, there's one brute force way to do this. Write down all the possible 36 ways and look at them and check each one off if it gives you an odd sum. You can do that. There's lots of ways. Let's do it this way. That uses what we'll call the addition principle. Let's divide it up into, well, how many ways can you get it? You can get a 3. That's odd, right? You can't get a 1 with 2 dice. So you can get a 3, you can get a 5, 3, a 5, a 7, a 9, or an 11. These are all completely separate possibilities. The addition principle says that if you can divide up the things you're trying to count into disjoint possibilities, then count them all separately and add them together. And if you're thinking, what kind of a principle is that? It's just complete common sense. Well, then good for you. That's all it is. It's just complete common sense. So let's add them all up. How many different ways, when you spin 2 dice, can you get a 3? You can get a 1, 2, or a 2, 1. How about 5? Right, everyone agree? 6? This kind of symmetry comes up a lot in counting, and there's often a lot more depth behind what you're doing, and you can discover it looking for patterns, but we're not going to do that now. We're just going to look at this, add it up. There's our answer, 6, 12, 18, half of them. I guess that's not such a surprise. Although, I got to tell you, I could easily come up with a problem where your gut instinct would be to guess half, and you would be wrong. So be really careful in counting. Your intuition does not always correspond to what happens when you really do the counting. Be really, really careful. Don't make kind of fuzzy arguments and expect them to work. Sometimes they do, sometimes they don't. All right, my next principle. We're getting a little away from whether the book has these 2 principles, and then it says, okay, here, now I'm going to teach you some basics. But I think there's more principles that the book leaves out. And these are the ones that anybody who gets good at these problems routinely uses. And I want to give them to you as principles so you think of them as part of your bag of tricks instead of having to just discover them by yourself. All right, the complement principle. The complement principle is one of the key things in counting. It basically says, look, if you can't count what you're trying to count, count the opposite. Because sometimes counting the opposite is easy. And what does that mean? Here's a simple example. How many of the dice that we just spun, how many are not doubles? How many are not doubles? Well, it's a lot easier to count the doubles than it is to count the not doubles. How many doubles are there? 6, right? 1, 1, 2, 2, 6. So how many were there altogether? There were 36 altogether, minus 6 for the doubles. That equals the not doubles. 30 not doubles. This is a very, very straightforward, simple example of this. But this idea is a fundamental idea that comes up all the time. Let me do another example of this. Let's say you're doing something, some random thing. Say I take this teeny piece of chalk and I throw it way over there on the other side of the room, and if it lands in that flower pot, I succeed. Oh, I missed. How often am I going to get that? 1 out of 100, say. Never. Let's say it's 1 out of 100. If not, I'll just move the flower pot down. Let's say there's something I do that's 1 out of 100 chance. And let's say I do it 100 times. So if you ask somebody who completely doesn't think about it for a second, or is very naive, they'll say, well, if you can get it 1 out of 100 times and you do it 100 times, I guess then you'll have to get it. I mean, that's not true, right? I mean, there's plenty of things you do, like say you're a 50% free throw shooter. Does that mean every time you shoot 2 free throws, you get 1 in? No, it doesn't mean that at all. It means in the long run, you'll get half of them in. This means in the long run, I get 1 out of 100 in. But if I do it 100 times, it doesn't mean that I'm definitely going to get 1 in. Well, what is the chance that I'm going to get 1 in if I do it 100 times? We're going to calculate this straight up. And this actually relates counting to probability, which is a good connection for you to have. We're going to do this problem right now with a complement principle. And it's not that hard. It's going to be a combination of the complement principle and the multiplication principle. All right, so what if I told you my chance of getting it on the floor is 99 out of 100? That's the same as the opposite of my chance of getting it in, or the complement of my chance of getting it in. Getting it in is 1 out of 100, missing it is 99 out of 100. Now you can do something that's a little bit better. What's the chance of me missing it twice? If I want something to occur and I want it to occur again, that and word is like I'm spinning this die and I'm spinning another die. If you want 2 things to happen, one and then the other, you can just multiply them together to get the count on it. So if I take 99 out of 100, that's a chance of me missing, and I want to know how many times out of 100 squared I will actually miss. It'll be 99 times 99 divided by 100 squared. That'll be the number of times I miss if I do it twice. Okay? What's the number of times I will, what's the probability or the number of times I'll miss if I do it 100 times instead of twice? I'll write this out. 99 over 100 to the 100th. This represents the chance that I will actually miss 100 times in a row. Okay? If anybody have a calculator? I can't do this in my head. Do 99 over 100 to the 100th. This is the chance we miss the pot 100 times in a row. It's the multiplication principle, one after the other after the other. What do you get?
You can't do that in your head. You can do it.
All right, but I don't want to. What do you get, Rob? 0.366 something. Okay, so that's a reasonable number, even though I have a strange-looking thing here, right? It means that I'm going to miss 100 times in a row a little over 1/3 of the time. So what's the chance I'm going to get it? It's the complement of this. It's 1, the certainty, minus this. So if I ask the question, I got 100th of a chance to get this piece of chalk in that flower pot. I do it 100 times. What's the chance I'm going to get it after 100 times? A little less than 2/3.
Let's get it at least once.
At least once, right. Get it at least once, right. This is a hard problem. And, well, relatively hard compared to this easy one here. And it uses just 2 ideas, the idea of complement and the idea of the multiplication principle. It also connects the probability, which I did a little early here because I want you to see it. And I'm going to come back to showing you the connection between counting and probability later. So keep this in mind as a good example. I am going to build up to this later a little more slowly. Questions?
You should also tell them why it's 37%.
All right. If you do this problem, instead of 100, you make it 1,000 at 1,000th of a chance, and then you do it 1,000 times, or 1/10,000th of a chance, and then you do it 10,000 times, then this number, this one here, becomes, and the other one becomes e minus 1 over e. That's the complement of this. This number, the chance of me missing, goes to 1 over e, that number that came from calculus. Where does it come from? It's not too hard to come up with this, but we're not going to do it now. I mean, it seems mysterious, but it's not so bad.
But as a practical matter, it comes up regularly in radiotherapy.
Oh, yeah? Oh, okay.
We have to know what doses are going to kill the last cell.
Mm-hmm.
And since it's the chance of any particular photon killing a cell is going to be just as much as the chance of a bullet hitting a cell is going to be the same after the cell is dead as before. So that we're going to be dealing with that.
A set of probabilities kind of like this. Huh. Well, that's very interesting. I do it for much more mundane things, like, no, really, like free throw shooting. You know, I say, or I do it with darts. I was going to challenge one of you guys to darts. I can get, if I shoot, if I'm doing well, I can get, out of 100 throws, I can get 17 in the middle. That's like a good day for me. I can get 17 in the middle. So then I have to calculate, well, what's the chance if I throw, say, 10 of me getting 2 or more? And I can calculate that probability knowing that I get 17 out of 100. It's a very similar calculation to this. And I know whether I can bet on this or not. If I got a 65% chance of getting 2 or more out of 10, then I can bet to my heart's content and I'm going to win money. If I just have a gut instinct that I can get 2 out of 10, your gut instincts about what you can do in life are hardly ever good to bet on. It's just not a way to go. You do a calculation before you go ahead and bet on what you think you can do. Let's move on to the next principle. We're reviewing principles here, not coming up with ABCs of counting yet. These are just the general principles, and then we're going to go through some more, I think, what we call how to spell. You know, kind of like, what are the basic notations and definitions. But right now, just principles are much more important. The next principle, we did addition, we did multiplication, we did complement, and now we're going to do a principle that I call counting double. Counting double in a controlled way. I don't really mean double here. I mean multiple counting in a controlled way. It's a really, really good technique. Here's one place you've seen this already. Say I want to count how many ways there are of choosing a pair of you to go up and complain about the leak in the corner. All right? I want 2 of you to go upstairs and complain to @stake, there's a leak here, go. How many different ways can I choose you? Well, I can pick anybody for the first person, that's 36. And I can pick anybody for the second person, that's 35. But if I pick Joe for the first person, and then I pick Tom for the second person, and they go up, and then my next pick is Tom first, and then Joe second, they're going to say, you 2 jerks were just here. Right? So that's not the same. I got to pick 2 different people every time. And if I just do 36 times 35, I've counted every single person in a pair twice. So the right number of pairs in this group is 36 times 35 divided by 2. But it's a nice way to count, right? I counted everybody twice on purpose, but I controlled it. I knew I was counting everybody twice. A lot easier than counting it the other way where you come up with the triangle numbers. Well, not a lot easier, but a little bit different. There are examples where this double counting is a lot easier. Let me give you one. All right, so this time, no more sending people upstairs to complain about the water. This time, we're getting political. We're going to get a president, a vice president, a secretary, and a treasurer for ADU. That's right, recount. Now, if I really want a president, a vice president, a secretary, and a treasurer, I've got 36 choices for the president. And multiplication principle, 35 for the vice president, 34 for the secretary, and 33 for the treasurer. And the order here matters. I mean, it's different if I pick Tom second and Joe first, then one's president, one's vice president. So here I don't want to divide by anything. I don't count anything double. It's actually 36 times 35 times 34 times 33. But what if I don't care who gets what title? What if I just want them to act as a committee? Okay, it's just a group. In that case, I've counted a lot of these things twice. Here's my count again. 36 times 35 times 34 times 33. And I'm going to write down one particular sequence of president, vice president, secretary, and treasurer. I'll just give you guys, here, we'll do Joe, Tom, Seth, and Heather. Kick his ass, Heather. Take a look at this. I counted this once. Look at this committee. Now I only care about the committee, right? So all the other possibilities that have J, T, S, H in them in a different order have been counted more than once. In particular, this one's been counted. This one's been counted in there as a separate case. Well, it's really the same. TJSH is the same as JTSH as far as the committee goes. How many different ways are there of counting this guy multiple times? I can rearrange it any way I want. 4 factorial. Right, we did that earlier. So I got to take this number and note to myself that every single one of these was counted 4 factorial times. So if I want to get the right number of committees, I just have to take this number and divide it by 4 factorial. Then I have each one of these possibilities as a committee counted just once. This is an idea you'll see again. It'll come up when we talk about the ABCs of binomial coefficients. But it's a really important idea. Count double on purpose. Count multiple times on purpose. Keep track that you've counted everybody 24 times, and then divide by 24 to get the real number you're looking for. It's much easier to count this way than any other way you'll try. Questions about this? That's counting double. One more principle before we move on to the nitty-gritties. One more principle. When are things the same? I think of all the principles, this might be the most subtle and the most important. One of the most common things you do in combinatorics is notice that counting this turns out to be the same as counting this, even though they seem completely different at first glance. And that's why I spent some time at the beginning of the day reviewing that question. You all looked in the previous problem set at the following problem. You're given 3 matrices, or n matrices in the general case, or 4 matrices, and you want to put parentheses around them to associate them and be able to multiply them out. So here's one way. There are plenty of other ways. How many ways are there? You all know, right? There's 5 different ways. You did this problem set already. Another thing, which seems like it's the same, but when you realize and you think about it for a while, it really isn't. Then you think about it again, you realize, oh, it really is. Are these balanced parentheses? Balanced parentheses of 3 pairs turn out to be exactly the same as counting different ways of associating 4 matrices. Give me 4 matrices. How do I associate them? How many ways can I do it? Same as the number of ways to write 3 pairs of balanced parentheses. These things are the same. It is not obvious they're the same. You have to think carefully and explain why they're the same. There's one more thing that's the same as these things, which isn't obvious. As I said before, the number of different binary trees with 3 nodes. Here's a couple of them. There's 5 of those too. All 3 of these obey the same recurrence relationship. All 3 of these have the same values for given number of nodes here and here, given number of nodes, given number of pairs of parens, and given number of matrices plus 1. They all have the same exact counting structure. Not obvious. Let me give you another situation like this when it is obvious, or at least at the stage where you are that you'll feel it's obvious. This is something you've seen before. The maximum number of edges in a graph with n nodes. Okay, I have a graph with n nodes. I want to throw in as many edges as I can. No multi-edges. Just 2 vertices or 2 nodes can be connected by an edge, yes or no. What is this the same as that we just talked about?
Number of pairs complaining about the leak.
Right. number of pairs chosen from a group. Choosing two vertices is like choosing a pair. Taking those two nodes from a group. Putting an edge is like sending them up. How many different ways can I choose these edges? The same as the number of ways that I can choose two people from a group. These two things are the same. There's something else that's the same as these things that you've seen dozens of times in this class already. And it's the triangle numbers. If somebody asks you to figure out what's the triangle number when you're trying to go up to a particular n, it's going to be the same as these two.
Say that again.
You want to know if I said it right?
I want to know if I heard it right.
I don't know if I said it right, so let's write it down. Let's do this example with 7. I got 7 people. I'm going to take pairs out. That gives me 7 times 6 divided by 2. Right? So that equals 21. Let's look at the triangle numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6. If I take the triangle number all the way up to the number 1 below the number of nodes in my graph, that's the same as that 21. That's not an accident. So this equals number of pairs from a group with n people is the same as maximum number of edges in a graph with n nodes is the same as the triangle number of n minus 1. All the same. Here you can actually convince yourself they're the same. There I think you really need some more practice before you can tackle that problem. The level of difficulty and sophistication in seeing that things are the same really varies a lot. You all know about binary trees. Here's binary trees. They spread out 2 each time. I'm going to define something called a funny binary tree. Here's a funny binary tree. Funny binary tree. Here's the rules about how you generate a funny binary tree. What did he say? Tell jokes, yeah. Tell jokes and wait. Here's how you build a funny binary tree. You, on the left side, split it into 2. And on the right side, only have 1 coming out. Leave off this right node. Let's continue this down to the next line. On the left side, it splits into 2. On the right side, it splits into 1. What about here? Let's do a couple more layers. Do you see how this graph is defined inductively? I describe how the next stage comes from the last stage.
2, 1, 2, 1, 2. 2, 1, 2, 2, 1.
All right. Everyone understand? Could you do the next level if I asked you? You could all do it. All right. Now let's look. How many nodes are there at a given level of this funny binary tree? 1, 2, 3, 5, 8.
I've seen that before.
Yeah. What's on the next level?
13.
13. Do you have any idea why it's the same as the Fibonacci numbers? Because you've seen it before. There's a good proof. I don't think it's obvious why this is the same. You can think about it. And you might be able to come up with an idea, but probably not on the spot at 30 seconds. But here's an example of something that's the same as this, that you wouldn't naturally notice that it's the same as this. How many different ways are there to write binary strings without double ones? Remember that from the problem set? The number of different ways to write binary strings without double ones is the same as the number of nodes in this tree. Now that I can convince you quickly. Every one of these nodes is going to represent a string of zeros and ones. Which one does this one represent? Left is 0, right is 1. This represents 0, 0. This represents 1, 0. How come there's no double ones at any node? Because I left out all the right moves after I made a right move. Anytime you go right, you can't go right again. That's how this tree is defined. No double rights. This tree's nodes represents in binary exactly the binary strings that don't have double ones. It's not obvious if I just described this tree to you and then gave you the problem with double ones that you'd even notice there was a connection after you worked on it for a while. But you got to look for these connections because each one shines light on the other. It's like walking around in a dark room and somebody keeps dimming up the lights until you get a better and better picture. All right, I won't do the proof of why this recursive relationship is true, but it depends exactly on the connection to the double ones. You all supposedly did a proof for the double ones, right? You came up with a recurrence equation. How'd you do that? You thought that there's the last case, either there's a 0 or the last case is either there a 1. You should have two cases. I can go over that problem maybe later on. But if you take whatever you did for that problem and connect it one-to-one to what works here in this problem, you'll see a connection between the number of nodes here and how they correspond to this set. So you take one problem, you see the correspondence there, you know there's a one-to-one with these binary trees, and you can take your argument there and transform it to an argument here. Even though you might not see the argument on the tree, and you might be able to see it with binary numbers more easily. Change your abstraction, and you can change what you can think about. It's one of the key ideas in scheme. Change your abstraction. It's not just makes things easier. It's that you couldn't even think of how to do it before. Now you can do it. Same thing in here. Same thing in combinatorics. Change your way of looking at the problem, and what used to be obscure becomes obvious. All right. I'm going to leave this. We can't do every little detail of stuff I'm trying to motivate with, but this is just motivation. We'll get to particular problems that I want you to work out soon. Questions about this? Yes, Tony. It's cool. All right. Isn't it cool? Yeah. Yeah, I think so too.
If you draw a large circle on the, oh goodness, the right branch of the tree, make the circle cut that line right. That's exactly the same as the left branch 1 unit up. So let's say a sub n is going to be a sub n minus 1 plus a sub n minus 1. Well, I was going to do 1 unit up. I was going to take in the top node.
Okay.
Taking everything else outside that, outside of the first circle. Those are exactly the same.
Good. That's a nice way to look at it. All right. That's it for principles. You all got the principles?
Check.
Check. Yeah. All right. They're deceptively easy. Be careful. They're really deceptively easy. Combinatorics is famous for, here's a really easy sounding problem that is really hard. It's also famous for really hard sounding problems that are really easy. Don't be afraid to engage yourself in the maze. Don't memorize stuff in this course. Do every problem, take your principles with you, and think about it. If you start to memorize, you'll kind of get lost. If you have to memorize, you can make it through, but try not to. Yeah, Anthony.
Can you explain real quickly again how you get the number on the denominator that gets rid of the double counts? Like, how do you arrive at that?
Yeah. Let's say A, B, C, and D is the group that I chose for president, vice president, and treasurer, secretary. But if I don't care about what order they're in, you know, if I want to count, for example, A, B, D, C as the same group, but I didn't, I counted them separately, then the question is how many things are counted A, B, C, D? How many of them are equivalent to this one that were actually counted separately? It's all the ones that have A, B, C, D in them in some different order. And how many different ways are there of counting A, B, C, D in a different order? It's 4 people. How many different ways can they line up? 4 times 3 times 2 times 1. So that means I could list, if I wanted to, 24 possibilities here. And every one of them was counted separately, even though I really want to count those 24 as just 1. And every single unique collection, A, B, C, D, gets counted 24 different times. So if I just take my whole big collection and divide it by 24, I end up getting 1 for each real unique group. Does that make sense? It's a really good question, and it's fundamental, and it seems so easy after you've thought about it for 10 years, and it's not easy. And I just got to tell you, just to admit my own, the reason that I like this part of the course so much, and the reason I spend so much time, or I feel I'm spending a lot of time, making sure we do it in a gradual way, is because this is the part of the course that when I first learned it 20 years ago was the most dense to me. It took me a long time when I first saw this stuff to really digest it and have it be automatic. But it'll come if you just spend 20 years, if you're me. But you're smarter than me, so it'll take you less. Yeah.
So if this was, these 4 were being chosen out of a group of 10, was it going to be 10 factorial over 4 factorial, or was it just 10 times?
If we chose this group out of 10,
Yeah.
we'd have 10
Yeah.
times 9 times 8 times 7, and then we divide it by 4 times 3 times 2 times 1.
So in the just picking 2 people out of a group of 10, it was just 10 times 9 divided by 2 factorial. Which is,
Exactly. Right.
okay.
And we're going to do this right now. What you're discovering right now, which is just perfect, it's like a pedagogical dream. It's like, we're doing this right away. You should exactly be thinking about these things. Once you have these principles, the next thing you discover are these things called binomial coefficients, which is exactly what Chris was asking about. And we're going to do that right now. And although these topics were talked about rigorously, maybe for the first time in the 1600s by Pascal, they were talked about on a very, very algorithmic and also somewhat rigorous way long before. Way back into the early Middle Ages, maybe 800 or 900, people were already talking about permutations and combinations. They didn't do proofs with it mostly. By the time 11, 12, 1300 came along, there were some proofs that you can find in Islamic and Hebrew mathematicians' works. And then nobody really knows whether or who looked at that stuff from this huge gap between the end of the Greek period and the beginning of the Renaissance in Europe. But there was clearly a transmission of information. It didn't just jump. There wasn't this dark period in math as people kind of think. There was definitely an evolution, and it worked its way, permutations and combinations having a very fuzzy but definite origin sometime in the early Middle Ages. All right, so people knew about this stuff a long time ago, and they did it for mysticism and for astrology and also for astronomy in all sorts of different ways. But we're going to do it today for computer science. Here's a symbol, PNK. We used PN before to mean the number of permutations or the number of ways to order n elements. So what this means is I want to choose k people from n people, and permutations mean that I care about the order, that I care who's president, I care who's vice president. So for example, P of 36, 4 equals 36 times 35 times 34 times 33. No division, because I absolutely care about who comes first. We just did that problem. This is a general way of writing it for any n that you start with and any k that you're choosing. And we're going to come up with a formula for this now that we understand the principle for the particular case. Questions? Well, let's write it out. The choice for the first one, how many choices do we have? N, right? Not 36, but n. And then the next one, n minus 1, all the way n minus k plus 1. Is that the last one? Let's just double check. Sam's right, of course, but let's double check. Let's double check. The last one here was 33. 36 minus 34 gives you 32. N minus k. Then you got to add 1 to make sure you don't go too far. Just make sure you get the detail right. Now, that's not usually how we write it. Although back in the Middle Ages they would write it that way. They just wouldn't write it with these symbols. They'd say it would be the product of all the numbers starting from 1, where you go in a downward direction, subtracting 1 with each subsequent number until you get to the lowest number, which would be k less than the number you started with plus 1. You could not figure out what the person was talking about unless you already knew the idea in advance, or you spent 5 hours deciphering it. So notation is very important. And it's clear that there were definitely mathematical works back in those times that for 100 years went completely not understood. It just wasn't clear anybody could make heads or tails out of them, unless the teacher actually was presenting it. All right, let's go ahead and write this in a better way. It's n factorial, right? It's everything, but let's divide out this part. And that'll give us what we have left up there. What's that part? No? Oh, I get n factorial divided by n minus k factorial. Does everyone see why this is the same as this? It's because you have the whole list of products, and then you want to divide through the stuff that would come later. That's the formula. Let's make a formula for the same issue, but we do not care now about the order. We want it to just be a group of 4. Same as before, but now this is called combination, so we say C of nk. And it's the same formula except for one thing. What do we do to fix this? Right now we have to divide through by, in this case, 4 factorial, or in general, k factorial, because we have counted each one of the things that we're trying to count k factorial different times. So we divide through by k factorial to make it work. This comes up more often than this, although they both come up a lot. This comes up in so many areas of mathematics that it's completely fundamental to know this and have it be as automatic to you as arithmetic. It's so fundamental and automatic that it has a special symbol. This and this are the same. And we say n choose k when we want to talk about this symbol. N choose k means that I'm choosing k things from n, and I don't care about the order. These things are called binomial coefficients, and you'll see why in a second.
Shay?
Yes.
Could you explain one more time why we're dividing by n minus k factorial?
Yes.
Permutation?
This n factorial takes n times n minus 1 all the way down to 1. I'm going to put this in for a second. This whole thing would be n factorial. And now if I divide through by this part to the n, I get the part I really want.
Okay.
Do you see that?
Yeah.
Good. It's a good question. Other questions so far? Okay, good. I had a 5th grade teacher who was a very nice man, but he was also a very strict guy. And this was in some Bible class I was taking about the prophets. And we were studying something, and he asked me, what does this word mean? It was a Hebrew word. And I hadn't the slightest clue what it meant. It was some kind of a verb, somebody doing something to somebody else. And I didn't know. So I was a good reader, even though I couldn't understand what I was reading. I could actually pronounce everything in Hebrew. So I looked down in the book, and there was an interpreter from the Middle Ages who had described the meaning of the word, because it was a strange word. And he described it in terms of other words that I also didn't know. So I hesitated for a minute, and then I kind of paraphrased what the person wrote, and I said it out to him. And I smiled at him, and he smiled back, and he goes, what does that mean? And then I started hedging, and I go, well, it's kind of like, I'm looking for a clue. He doesn't give me, he's like stone-faced, no clue at all. And I go, well, like when somebody wants to tell somebody something, but they don't want to tell them, straight up. They want to kind of like tell somebody else first, and they're, you know what I mean? He goes, oh, you mean like he related it over to somebody else to tell this guy? And I go, yeah, that's right. And he goes, wrong. So I always remember that, and I never do it because I remember feeling like such an idiot. I go, I trusted you. Let's see this problem. What's the coefficient of x cubed in x plus 1 to the 7th? This seems like a completely unrelated problem, but it's completely related to this point. And I want to run through this with you because in going through the answer, you'll understand the connection between this counting idea and this question, and you'll understand why these things are called binomial coefficients. So here it is. Here's x plus 1 to the 7th. 1, 2, 3, 4, 5. This chalk is great. It's so much better than that other lousy chalk.
You write faster now.
I feel good. I'm moving. It's good chalk. And it's not dustless. It's dustful chalk. That's what makes it work.
Now multiply all those out with that chalk and you'll give it a good run.
We're not going to multiply it out, but we are going to do this. Right, it's hideous to multiply this all out. Nobody wants to do it. But what you can do if you write it out this way is notice that any one of the terms, if you did multiply it out, can be written in the following way if I keep track of what x's I'm dealing with. So I'm going to write x1 here just to keep track. x2, x3, x4, x5, x6, x7. And let's multiply through an example. I could get x1 times x2 times 1 times x4 times 1 times x6 times x7. I can just multiply through, and as I go along, left to right, I can choose either to multiply through the x part or the 1 part. Now let's try to write down, as I do that, which ones end up having 3 x's in them. Because those are the ones that will accumulate to eventually giving me all the x cubes. Well, let's write them down. Let's start writing them down at least. x1, x2, x3, 1, 1, 1, 1. Okay, that's 1. That's 1 x cubed. What's another one?
x2, x5, x6.
Thank you. It must have been so much fun to grow up in your house. That's
My children left home as quickly as they
I was going to say, the dinner table must have been a puzzle just to get to the peas. Children, you've noticed today that I've set the main course up locked away from the appetizer. If you can get it within a minimum number of moves, it really would have been fun. Here's another one. Every one of these combinations of x's and 1's multiplied together as you go left to right corresponds to 1 x cubed. So I could list these out and exhaust them, but that's just what you don't want to do in counting unless you're desperate. You don't want to go the brute force way. Okay? If you're desperate, you do it. But we want to figure out a way to count these more easily. What is this? There's 7 places here, right? Imagine that they all had 1's in them. What we're really doing is choosing 3 of those 1's to get replaced with x's. How many ways, if we have 7 1's, can we choose 3 of those places to throw x's? 7 times 6 times 5. I don't care about the order, right? If I pick x6 first and x2 next and x5 last, that's the same one. I don't want to count that twice. So I don't care about the order. I care just about choosing a collection of 3 places from 7. That's exactly the same as 7 choose 3, which is exactly the same as 7 times 6 times 5 divided by 3 times 2 times 1, 35. So you can see it would be good, because we take 35 ways to exhaust this. It's better that we do it this way. That means there are 35 ways of multiplying these terms together and getting 3 x's in the resulting term. That means there are 35 pieces of this multiplication that will have x cubed. So the coefficient in front of the x cubed is going to be 35. Right? This is an important problem to look at. It connects counting back to algebra. All right, let me stop for a second. Tara and I did a card trick at the very beginning of this year, which you are going to see again in this kind of the roaming problem set that I put up there that needs to be done by the end of the year. And this, I know what you're thinking. You're thinking he said year instead of month. This problem had to do with you choose a set of 5 cards. My assistant looks at your 5 cards, doesn't show them to me, picks 4 of them out, and then hands me 4 of those cards in order so I can see what order they come in. And then I look at the order of those 4 cards, and I determine the 5th card that's in your hand. And this is not a magic trick, it's just a combinatorial trick. You can make it look like magic if you patter it up a lot, but it's completely a mathematical trick. We're going to do that again, but before we do it, not today, we won't do it, but we'll do it soon, next couple days. Before we do, what I want to do is show you part of that problem and analyze it combinatorially. How many different ways are there for you guys to choose the 5 cards to begin with? How many different sets of 5 cards could show up in your hand if I start with 52 cards in a regular deck and I let you choose? It doesn't matter what order you choose them, right? It's just the collection of cards in your hand. So it's 52, choose 5. That's 52 times 51 times 50 times 49 times 48 divided by 5 times 4 times 3 times 2 times 1. Right? That's the number of different ways you can choose cards. All right. Now, out of all those ways, then, oh, here's my assistant. Then Tara picks, is that you? All right. I got my glasses on. So Tara picks 4 cards out of that collection. How many different ways, given a hand of 5 cards, can she choose 4 and show them to me in order? This requires a little more thinking. Once she chooses the 4, how many different ways can she hand them to me in order? Once she chooses them. 4 factorial. 4 times 3 times 2 times 1. But she gets to make a choice before she shows them to me in order. She gets to choose which 4 she's going to show me. How many ways are there for her to choose those 4? 5. Choose 4. That's 5. Right? She has 5 choose 4 ways of picking the 4 cards. And for each one of those, remember the and for each one, the multiplication principle? For each one of those, she has 4 factorial choices. So it's 5 times 4 factorial, which equals 5 factorial, or 120. That means when Tara sees your hand, she at least theoretically can transmit to me how many pieces of information? 120 different possible pieces of information. She can give me 120 different possible sequences of cards. Since there's only, well, 1 card left in your hand, presumably, with 120 pieces of information, I should be able to determine the card left in your hand because there's only 48 cards that I don't see. I even seem to have a little bit of slack. So at least theoretically, it looks like we could do this puzzle. And we'll get back to this puzzle again, but I wanted to immediately show you the connection between what you just learned with combinations and permutations. It relates immediately directly to analyzing that puzzle, that magic trick. Questions? All right, we're moving along. You guys are cooking with gas. This picture here is sometimes called Pascal's triangle. Pascal didn't actually invent Pascal's triangle. A lot of people had pictures of it in their works long before Pascal. Sometimes when I give talks on my own research and history of math, I show some weird script in Hebrew with this funny weird diagram that looks like it's Pascal's triangle. Actually, it's just long division. And I ask any group of mathematicians, hey, what do you think this is? And they all guess Pascal's triangle. And I go, oh, no, it's just long division. And they all look at me like, we wanted Pascal's triangle. But it shows up everywhere. You can get in almost every culture, Pascal's triangle shows up. It's very, very fundamental. You can find a lot of stuff in it. Not only the binomial coefficients that I just told you before, but all sorts of other relationships. The Fibonacci numbers show up here in an interesting way that you'll see in your problem set. Almost everything you've seen in some way shows up here. Where are the triangle numbers in this picture? Anybody see them?
The third diagonal number.
Triangle numbers. Well, what is this weird picture? And why does it have so much symmetry and beauty and combinations? It's just got so much in it. This picture is supposed to represent the binomial coefficients of all the possible values of n and k. So for example, let's take this row. This row is 2 choose 0, 2 choose 1, 2 choose 2. 2 choose 0 is, oh, what is 2 choose 0? How many ways are there of choosing nothing from a set of 2? Well, there's one way to choose nothing. You choose nothing. So there's 2 choose 0 is 1, 2 choose 1 is 2, and 2 choose 2 is 1. The next row is 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. It's a table of all the binomial coefficients. Everybody okay so far? I want to show you a theorem which is known as the binomial theorem that relates to this and relates back to the algebra we just did. And then I'll talk a lot more about this triangle. Here's the theorem. There's a lot of versions of the binomial theorem. Here's one version. If you take two things, x plus y, and you multiply them out n times, kind of like this x plus 1. Okay? This is a special case of the binomial theorem. Here's what ends up happening. First I'm going to write these terms out. X to the n minus 1 y, x to the n minus 2 y squared. The first thing that happens is, I need more room. I'm going to rewrite this, sorry. X to the n, what's so funny? It's not so bad. The first thing that happens is you start with x to the n. You'll know you'll get that term. You'll also get terms where there are n minus 1 x's and 1 y. You'll also get terms where there are n minus 2 x's and a y squared. Anytime you multiply these things n times through, you're going to get some number of x's, some number of y's, but the combination of the x's and y's together have to add up to n, just like the combination of x's and 1's here had to add up to 7. So if you notice, I got all x's here, I got all x's except 1, I got all x's except 2, and this goes all the way down to, what's the second to last term? X, y to the n minus 1, and then y to the n. All right, so that part's okay, but the question is what numbers come in front of each of these terms? Remember here, in front of the x cubed 1 to the 4th term, we got 7 choose 3. So the binomial theorem tells you that this is general. And here's what comes in front of each of these terms. In front of here comes n choose 0. In front of here comes n choose 1, n choose 2, n choose. Good. Was that you, Joe? Yeah. Good for you. And then n choose n. You see these numbers? N choose 1, n choose 0, n choose 1, n choose 2, all the way up to the end? They represent a particular row in this triangle. So if I want to know, for example, what's x plus y cubed? All I got to do is write these out. X cubed, x squared y, x y squared, y cubed, and copy these numbers over. 1, 3, 3, 1. Who gets this? Half of you? 2/3? The binomial theorem gives you a way of taking expressions like this and splitting them up into pieces. It's deceptively useful. It looks like it makes things more complicated, but it often makes things easier. You're going to see it come up later on. I want you to see it today because it connects to this nice example of permutations and combinations, and because it relates to this triangle that lists all the permutations, that lists all the combinations for every n and k. All right, let's make sure everybody gets this. What if I have here 1 plus 1 to the n? Okay, let's use the binomial theorem. It equals 2 to the n. You're all laughing. You're right, it equals 2 to the n. What does a binomial theorem tell you that it's equal to? The x's and y's here are all 1s, right? So they all become 1s. That's a nice example to use. You don't have to worry about the x's and the y's. They're all 1s. X to the n is 1. X to the n minus 1 is 1. Y to the anything is 1. So what do you get here? N choose 0 plus n choose 1 plus all the way up to n choose n. And that equals 2 to the n. Well, that's neat. That came out for free. This is one of the basic combinatorial identities. There's dozens. There's 100 of these. Don't memorize them. Well, this one you can memorize if you want to.
That's another nice one.
What? Which one?
1 minus 1.
All right. I'll go for it. Who knows what happens if we run through 1 minus 1?
Get 0.
You get 0, right? what's the series going to look like?
The opposite terms are negative.
Every other term is going to end up being negative because these negative ones multiply, and when you have an even number of terms, you get positive, and when you have an odd number of terms, you get negative. The number of terms change 1 each time, so they start equal to minus, plus, etc.
So the NC evens equal the NC odds.
I don't know if this is plus or minus, huh? This is negative. That's neat. So if you alternate the terms, well, that means we can, let's check this out. This should equal 2, this should equal 4, this should equal 8, right?
No. It's not necessarily negative.
It depends on the end, right?
Depends upon whether n is odd or even.
I'll put a question mark here. Depends, right.
It's got to be positive.
2, 4, 8 if you add them. This should be 16, is it? Better be. Now let's do the other trick. 1 minus 5 plus 10 minus 10 plus 5 minus 1, that should be 0.
Well, that's because it's symmetrical, but go up to the 16 row, and that's impressive.
To this row?
6 plus 1 equals 4 plus 4.
1 minus 4 plus 6 minus 4 plus 1. 0?
Right.
More impressive. Agreed. This is symmetrical, not so fancy. This is less symmetrical, more interesting. There's a lot of hidden cool things in the binomial theorem. We're going to touch on them later.
NCN minus k, that's another impressive one. It's completely symmetric.
What do you think the squares of these things equal? For another day.
The square of n0 or the square?
n0 squared plus n1 squared plus n2 squared. Adding, instead of just adding up the regular binomial coefficients, n choose 0, n choose n, we'll square them each and then add them up. That's all right. You'll see it on a problem set. That's okay. I want to go back to this triangle and point out a feature that you might have noticed or you might not have, and it's something we can prove. We can prove it in 5 different ways. The styles of proofs are going to be things you're going to see again and again, so I want to concentrate on at least 1 or 2 of these kind of proofs. One of the proofs will be a proof by induction, which I won't do because we're sick of it, right? We don't need to do more proofs by induction, but you could, and I'll mention that you can. But what is it that we want to show? You can write, how did I write this out so fast? Did I go ahead and do the factorials in my head? No. To get the next number, like 3, you add the 2 that are on top of it. So the 10 is a sum of 6 and 4, and 15 is a sum of 10 and 5. And the 1s, you just imagine there's zeros all the way on the outside, like a sea of zeros. So 0 and 1 gives you 1. You always get 1 out here. So the next row would be 8, 28, 56, 70, 56, 28, 8, 1. It's a nice, easy way to do it. Let's write out what that means now that we've noticed it. It means that n choose k, take a random one, say this one, n choose k equals this one. What's this one? N minus 1, because it's the row up, and it's 1 to the left. So this is n minus 1, k minus 1, plus n minus 1, k. Back 1 and then up straight. Let's look at this a second. We haven't proved this yet. We just noticed that it was true. One way to prove this, and I'm going to leave it to you if you feel like, because it's a very boring way, is you have formulas for all these 3 things, right? And factorials. Plug them in, see if they're all the same. You can all do it. And that would prove this formula. And it would be a perfectly fine proof. Everyone agree, right? It's just going to be a bunch of factorials. You mush them around. Let's do it a different way. So there's proof by formula. Check. There's proof by induction. Yak. Actually, in this example of proof by induction is not so easy, and it doesn't scream, and it's not natural, and it's hard. You get these ugly things when you try to prove it by induction. So it's a good thing we're going to leave that there. But we're going to prove it by combinatorics, by counting. Proof by counting. This is an important method to learn. Woohoo! Let's do this proof by counting. I'm going to show you that if we think about this in terms of how to count it, that it's the same as if we think about the sum of these two things as far as how to count them. This is that same idea of what things are the same. Counting this many things is the same as counting this and this together, adding them together. Let me convince you of this. The best way for me to convince you is with a particular example, and then convince you that that example really used none of the specifics to convey the idea. So it will really be completely general.
Shouldn't have erased x1 plus 1, x2 plus 1, x3 plus 1.
How come?
You could have added an x8 plus 1 and then shown.
I could have, yeah. But I like to pretend I'm doing new stuff at least. Let's see. Yeah, let's do it like this. I got 7 things. A, B, C, D, E, F, G. I want to choose 3 of them. I don't care about the order. How many ways are there to do it? 35 ways, right? 7 times 6 times 5 divided by 3 times 2 times 1. I want to divide these ways up into 2 categories. Some of the ways, there's a very special individual in these 7. Let's say they represent people. Okay, so say A is that woman down in Florida that gets to decide who becomes president. Everybody else is just some schmuck. Doesn't matter. There's an important person in everybody else. So what happens? I have to choose 3 of these people for my committee. So in my head, I'm thinking about, well, there's 2 possibilities. Either I include the person, who can push the button on who's president, or I don't include her. Right? Some of these committees of 3 will include her, some won't. Everybody with me? How many committees include her? She's included. How many committees include her? If I include her, then I can include just 2 more people. I include those 2 people from 6. This represents the big wig is included. Okay? But that's not all the possibilities. Let's do the rest of them, where I do not include her.
6, choose 3.
If I don't include her, that she's out of the picture, I have 6 left, but now I have to choose 3 from those 6. N choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k. There's nothing I did here that was specific to 7 and 6. If I had written it up with n's and k's, it might have been a little less clear, but writing it up like this doesn't make the argument any less general. There was nothing I said that really relied on 7 and 6. This list could have gone on forever, and your answers would have been just the same in terms of the n's and the k's. So let's call that a proof. Check. That's a proof by a combinatorial argument. Let's do this by combinatorial argument. Okay? We know this is true by binomial coefficients. Let's do it by a combinatorial argument, by a counting argument. Michael?
You're making an argument with one set of numbers, and that qualifies as a proof for the entire thing?
Mm-hmm.
In this class.
Me and Euclid. I'm arguing that I didn't use anything particular to 7 in this argument. You want me to write it out the other way? No, I'm not being facetious, but I'll write it out the other way, and you tell me if it's more clear. Here are my elements, x1, x2, xn. Let xi be a randomly chosen element. I'll keep talking, I'll stop writing. Be a randomly chosen element where I is between 1 and n inclusive. Then I claim the number of ways to choose k things from here is divided into 2 subsets. The subset that contains xi and the subset that doesn't contain xi. The subset that contains xi, how many ways are there to do that? There's x n minus 1 things left, and I have to choose k of them. So it's n minus 1, choose k. And the subset that doesn't contain xi, did I do that right? K minus 1. And the subset that doesn't contain xi, I still have n minus 1 things left, but I have to choose k of them. So I would write it all out like that. It would take me a half a board, and it would still be just as general. So I'm really not kidding about it. I mean, I'd have to write it out more detailed to meet a 20th century audience. But the issue is, have I convinced you that this argument is in general? And I didn't use anything for 7 and 6 that were particular, so I think I did.
Although you did assume a particular A. I mean,
right. And
if
you can pick any one you want. You didn't have to pick a random one. You can say pick the first one. It doesn't matter which one you pick. The whole thing goes through. You can choose anything. You have a lot of choice. It doesn't have to be my adversary that picks it.
7 times that many possibilities, because there's that many possibilities when A is the one that we're concerned with, and then there'd be that many when B is the one we're concerned with.
No, there wouldn't. If I pick A if I choose A as the one I'm going to focus on, then all the possible collections of 3 committees of size 3, either include A or they don't include A. That takes care of all of them. I could divide it into another 2 possibilities where they either contain B or don't contain B, but those 2 groups of 2 sets would overlap a lot, and I certainly don't want to count them all. Okay. So I can, and it's okay, and it's a good idea to focus just on one of them. It makes the proof easier. So I can tell that I didn't convince everybody of the truth of this, but I'm not going to do it in more generality, because you can find this proof.
You convinced us the truth of it. You didn't convince us that if I put that on my problem set, yeah, credit for it.
You know what? If you really wrote it down in complete English, and then you said, and there was nothing here, that where I used the 7 and 6, so this is a completely general argument, I would accept it. Absolutely. Let's go back to here. Let's try to prove this in a bunch of ways. We proved it by the binomial theorem. That was cool. We could try to prove it by induction. We could try to prove it by formulas. Right? You could plug in the formula for each one of these binomial coefficients and add up that whole list of factorials and get 2 to the n. That seems ugly. Or we could do it by combinatorics. All right. Ding. No. Ding, ding. You know where you're going to do it? On the problem set, you're going to do it by combinatorics. But today, I'm backing up. We're doing the yuck. I'm going to prove this to you by induction. Oh, you're thinking. No, it'll be good. Let's assume this is true. It'll be good. Let's assume this is true. Let's try to show that the next case is going to be true. I'm going to write down what we're going to try to show over here. This is the kind of induction you all like, because the thing you're trying to show and your assumption look like formulas. So it's easier to get a handle on where you're coming from and where you're going to. This one, that this equals 2 to the n. Here's our assumption. This works for all n. You can check that if n is 1, it works. Right? If n is 1, it's just n choose 0. It's 1 choose 0 plus 1 choose 1, and that's 2. And so there's a base case.
If n is 0, it works.
If n is 0, it works. Then it's just 0 choose 0, and you get 1. That's okay. How do we do it in general? We're going to try to head from here to here. You're not going to hate this proof. I promise. This is what we want to prove. Everyone agree? I just took the formula before and I replaced it with n plus 1. Not that I know this is true. I don't know it's true. I know this is true by my inductive assumption, and I'm going to try to prove that this is true.
No, we want to add an n plus 1 over Cn plus 1. The last term is.
Oh, n plus 1 over n plus 1. Right. Thank you. Right. Oh, and now I'm missing a term. There we go. The wonders of chalk. Right. High tech. Can't make any chocos. All right. What's next? We want to get from here to here, or from here back to here. Some connection between these two. That's just, you can't just plug in n plus 1s here and expect this theorem to still work. That's what we have to prove is true. But we can make a relationship between these ugly things and hopefully these things by using this. Let's fiddle with this until it looks like that. What's n plus 1 choose 1 according to this identity? It's n choose 0 plus. Right. Why did I think of using this? Because it takes things with numbers up here and converts them to binomial coefficients with numbers that are 1 less. So it gives me just what I want, a connection between here that has n's on the top and here that have n plus 1s. This one, what happens if I try to do it on this one? Why did I start on the second one? You get some negative number, right? What the heck is a negative value in a binomial coefficient? Well, your book will go ahead and define what that means so that it works in some other cool problem, but we don't go down that road. So if you see that in the book, skip it. Negative binomial coefficients are really cool. They do a lot of neat things, but we didn't have enough time. So we're not going to define them. We're just not going to do this. We're just going to copy it down. But notice, is n plus 1 0? Isn't that the same as just n choose 0? So if nobody minds, I'll just change it to n choose 0. And now what about this guy? What does he turn into? n1, n choose 1 plus n choose 2. Everybody see what's happening? I'm going to go down the whole way this way. N choose 2, n choose 3. Double, 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 double. What happens at the very end? Is Joe right? N choose n, n choose. Can we do that? No. Sorry. There we go. Magics of chalk again. Those are the last two.
Except for n plus 1, n plus 1.
Oh, right. Except for the. No, I did this one.
The last one is n plus 1.
Oh, I see. What's the last one? It's just fine. Well, n plus 1 choose n plus 1. I'll just make that n choose n because it's the same. These two are special. Everything else gets doubled. Everything doubles except for the two n's. Now look at the bottom. The bottom is exactly twice this. That means this whole thing is 2 times 2 to the n, and that's equal 2 to the n plus 1, and that's what we want to prove. So this induction proof is actually very nice. It's not bad like I said the other one would be. It's actually very nice as long as we have this relationship in place. Doing combinatorics is like doing a jigsaw puzzle, and the more people you have, which means the more tools you bring to the table, the more everything fits together and the faster it fits together. And it takes time to develop all that stuff. But you'll do it. You'll be good.
Clarify why you were able to simplify n choose n plus 1 to being just n choose n. I buy it for the...
n plus 1 choose n plus 1. How many ways are there to pick all of the things from all of the things? There's just one way.
One more in it. You can't... How can you choose...
If I have 7 people and I'm...
Can you choose 7 things out of 6 things? Isn't that
You
what's in
no.
there?
No. 7 out of 7 is the same as 6 out of 6 is what I'm saying. If you run through this formula, you get...
Oh, but it's not
He's
n
not
plus
applying
1.
the formula
It's
to the
n.
end.
It's n and n plus 1, isn't it?
But I'm not... You're right. You're right, Doug. That would be a problem. But this is the last one that I doubled. This one gave me these two.
Gotcha.
The 2 on the ends, I don't double up. The 2 on the ends, I just write down the way they are. Good question. I mean, that's important to clarify. I was a little fuzzy when I got to the end here because I messed up a little. But you're right. The 2 ends just go through the way they are, and that's why I get the double n choose 0 and the double n choose n. Comes from those 2 ends being copied down. So isn't that a neat inductive proof? That's powerful, right? That's... Yeah, go right to your grandkids. Hey, kids. All right. One more example today, and I'll let you go. We did a lot. One more example of a combinatorial identity that we can prove in a lot of different ways. One way you can prove this is by substituting in formulas with factorials and doing algebra. I know you guys can do it. We won't do it here. Plug in 2n choose 2, n choose 2. n choose 2 is n times n minus 1 divided by 2. 2n choose 2 is 2n times 2n minus 1 divided by 2. You can just put in the formulas and get algebra. Who thinks they can do it? Raise your hands really high so I know you really can do it. You want me to do it? Well, if you want me to do it, raise your hand. If you want $100, raise your hand. Just making sure. Just making sure. All right. That's one way. You could try to prove it by induction. That's another way. We really won't do it that time. But I want to do this with a combinatorial argument again. I want to show you that counting this number of things is the same as counting this number of things. So the way to show that two formulas are the same is to come up with something where counting it one way gives you this and counting it another way gives you this. It's a really useful technique because it not only lets you prove things like this, but it gives you a better way of looking at the same problem from two different angles. You're checking whether it's true?
No.
Oh, you got the proof.
Thinking through it.
Okay. Okay. All right, I'm going to try to do this proof more generally, since Michael didn't buy my more specific proof last time. I got an even number of things here, and I'm choosing 2 out of them. Since it's an even number, in my mind, I'm going to divide it into 2 halves. Okay, 1 half I'll call the A half, and 1 half I'll call the B half. And each of A and B has how many things in it? N. N elements here, N elements here. And I have to choose 2 things out of these 2n things. That's 2n choose 2. Now I'm going to show you another way of thinking about how to choose 2 things from an even number of elements. And that second way will be equivalent to this. Let's do it. I got 2n things. I have to choose 2 out of here. I'm going to divide up the possibilities into the following categories. Either my 2, let's make this a little more motivated. Okay, so I got 2n people. Half of them are men, half of them are women. I got to decide whether I'm going to pick 2 people of the same gender or 1 of each gender for this committee. All right? That divides up the category into 2 parts. The committees that have 1 man, 1 woman, and the committees that have 2 people of the same gender, either 2 men or 2 women. All right? How many ways are there to choose committees that have 1 man and 1 woman? I'll give you a hint. You could have done this before you started today's lecture. I got n choices from here. Well, maybe not before, but after 5 minutes. N choices from here and n choices from here. I can combine them in any way I want. If I have 3 men, 3 women, I can take any one of those 3 men and combine them with any one of the 3 women. It's like spinning 2 dice. 1 with n men, 1 with n women, and I get n squared possibilities. That's this. 1 man, 1 woman. 2 men enter, 1 man leaves. Where does that reference come from? It's a Mad Max movie.
This is the Thunderdome.
Oh, some of you watched that. It's Mel Gibson. He does Shakespeare. Let's do this one. Now I got 2 men or 2 women. 2 men or 2 women. So if I'm going to pick 2 men, I got to pick them from this set. How many ways are there to choose 2 from this set? N choose 2. That's men. How many ways are there to choose 2 women? N choose 2. They're completely distinct here. They don't interfere with one another. So 1 man, 1 woman, n squared. All men, n choose 2. All women, n choose 2. Altogether, 2n choose 2 plus n squared is the same as choosing a pair from 2n. It's another combinatorial argument. It's a very, very useful trick to get under your belt, to be able to think about 2 things in a different way, counting them the same. Yeah?
So you can add that together and get 2n over 2 is?
2 times n choose 2. This just means 2 times this. 2 of these.
More generally, n plus mc2 equals nc2 plus mc2 plus n times n.
True. All right, we're done.